We have been discussing about NMR quantum computing. We have gone through the basics of how NMR operates, its basic spectroscopic ideas, how it has become such a popular device of a spectrometer to start with. Now, we will be looking at it in terms of quantum computing, how the quantum or the qubit representation comes, and we discuss from there. So, the qubit representation for the NMR quantum computing. Actually, in general, the first few may not be exactly for just NMR, it can be for any case, is that a single qubit has the computational basis which is given as the 0 1 kind of representation, and that takes on to the states. So, the computational basis is based on the states 0 and 1. The wave function is represented as a combination of the basis sets 0 and 1. So, the alpha and beta represents the corresponding amount. So, alpha squared, beta squared mod are the corresponding amounts of alpha 0 and 1 state, that is their basis states which are there in the final state. So, in terms of how it is represented, we have already discussed. This is how it looks like, that it is a block sphere in which we have the state basis sets with certain proportional representation probabilities of alpha and beta square which are being used. So, at any point of time it will be alpha squared plus beta squared is equal to 1, that is the total amount of amount which is there, which is what happens when you make a measurement. It will give rise to either 0 or 1 with the probability which will be represented by their individual amounts, and so that is always is the final constraint that exists when you are looking at the qubit representative. So, a single qubit will be represented by the individual basis sets which will be constrained by these parameters. All possibilities exist, however, whenever the measurements are made, that has a probability of one versus the other in the way that the constraint has been designed. Now, for a 2 qubit representation, we have similarly the tensor product of these individual states, which is represented by 0 0. If it is any one of the other, then it is represented in this fashion. So, this is one kind, this is when it is of the other kind, and depending on the fact that we can distinguish between one this with respect to this, we will have the different 4 different possibilities. So, these are the 4 different possibilities, and they have their own probabilities of their existence: alpha squared, beta squared, mod of alpha, mod of beta, mod of gamma, mod of delta, and some of them would always be equal to 1 because the total probability has to be 1. So, in general, for n qubit quantum computer, we have 2 to the power n states, basis states, and they can be represented therefore by the wave function which would be having all possibilities of their independent basis sets with the alpha I as their particular contribution. So, that the probability of each of them being present is alpha I squared sum over all of them. So, this is how the qubit representation goes. We can, in case of the nuclear spin Hamiltonian, which is what we will be using in case of NMR, for a single spin the Hamiltonian is given by the interaction that we just talked about, the energy gap h cross gamma b 0 I of z, which is equal to minus h cross omega naught I of z equal to minus h cross omega naught over 2 minus h cross omega naught over 2 plus h cross omega naught over 2, and this is the Hamiltonian that we work with. For multiple spins without coupling, it can be simply written as a continuous form of the same way, where this is the delta I is the interaction is the shielding due to each of them. So, this is the shielding as we had discussed due to the other electrons present, and we can have the final Hamiltonian in the same format. There are, as we mentioned, when the field intensities are higher, there are these coupling terms which are due to the spin of each of them, which comes in separately, which is the Hj. So, in most cases the total Hamiltonian is thought of as the spin coupling term independent H naught with the coupling term spin coupling term, which is H of j. This is how the total Hamiltonian is looked at when you are looking at the nuclear spin Hamiltonian. If you go ahead and do calculations with this and look at the resonant conditions and solve how the populations change for each of these states, the excited state versus ground state, you will find that they basically oscillate between the ground and the excited states, and they go through these Rabi oscillations, where the area under the applied field is the one which determines how it is going to go into the excited state or not, and it is going to go back and forth between the ground and excited state. That is because the two states are coupled such that going into one case with the right amount of energy would also mean that when the energy exists for a long enough time, it will also be able to bring it down, and so on and so forth. So, it can flop, and that is the Rabi flopping principle, excited state energy, and depending on how it is applied, all these kinds of parameters can be looked at. This is a particular case where the shape of the field is hyperbolic secant. This is supposed to be one of the exact solutions. The Gaussian is another way of looking at the field. There are rectangulars applied field, which is also done. Mostly the assumptions are rectangular because you turn on and turn off, but nothing can be perfectly rectangular. So, some of these other cases are also being looked at. In terms of how this works, the steps involved in the NMR quantum computing, we have an initialization step. That is because before the computational starts, the qubits must be initialized to a well defined state. So, that is our initialization step. The information is then processed by applying unitary transformations. So, once the initialization is properly done, we are having our quantum register, and once we have our quantum register which has the information in that set that we want to start our computing in, we apply the unitary transformations one after the other. So, the first step would take it to the application of one unitary transform into the other, and so on and so forth, and the end of the computation the result is processed, and in the readout process processed in the readout process. So, this is our final readout process which has been looked at as the final output. The initialization process for quantum algorithms generally assume or demand that the qubits can be prepared in a pure state, usually in the ground state. Nuclear spins are in thermal equilibrium at room temperature and are subject to a reasonable static magnetic field in a highly mixed state, and is given the density matrix. And so, this is a situation where generating a perfect pure state, which is basically the perfect ground state, is a very hard job. and so it requires creation of effective pure states with a density matrix of the form of something like that, where it is not exactly all of them are in the ground state, but it is done in such a way so that they effectively are able to generate the same kind of result. So, in reality all the spins are in the same direction is what a pure state is supposed to be. Essentially you want everything to be alpha, but so that is sort of like what you would be wanting. So, if you are talking about 2 spin case, you would like all your 4 states to be at the 0 condition. The pseudo sphere state is the one we create a state in which all levels except one have equal population. So, basically this is the condition where we can actually have a situation where everything, if they can be balanced out, then all the levels except the one have equal populations, then it mimics a pure state, because that is the state which essentially has the property which is not going to be the same as the others, and therefore, that pseudo pure state was pretty much the same way as a pure state would have occurred, because the other populations are balanced out in terms of having equal populations. Because all energy levels except one have 0 population, such a state is very difficult to produce in case of room temperatures for NMR condition. So, the pure state technically demands that the trace of rho is equivalent to trace of rho squared, which is equal to 1. For a diagonal density matrix, this condition requires that all energy levels except one have 0 population. Such a state is difficult to create in NMR. So, what is done is that under high temperature approximation, pseudo pure states are taken, where we create a state in which all levels except one have equal populations. Such a state mimics a pure state. So, for example, alpha can be a very high number in this case, for instance, but as long as it is not going to create a issue, it is going to work out. So, for a 2 qubit system in equilibrium, we can have this situation where the pseudo pure state would therefore, the equilibrium condition is like this, where every possible case is existing, but the pseudo pure state is the one which will work for us, where it is 4000, it is going to work out for us. How to create this can be done by spatial averaging, temporal averaging, logical labeling, or spatially averaged logical labeling principle. So, methods for preparing effective pure states therefore can be done by logical labeling, which consists of applying a pulse sequence that rearranges the thermal populations such that a subset of the spins is in an effective pure state, something like this. So, for instance, there is some molecule penta, fluoro, butadienyl, cyclopentadienyl dicarbonyl complex in thermal equilibrium. The same spectrum after preparing an effective pure state looks like this. This is courtesy of some of the work which has been carried out in IISc Bangalore by Professor Anil Kumar's group. So, again there is another way, which is temporal averaging, consists of adding up spectra of multiple experiments. Each experiment starts with a different state preparation pulse sequence consisting of C naught and naught operations, and then there is spatial averaging case, which uses a pulse sequence containing magnetic field gradients to equalize all populations. Now, these are all practical principles for us when we want to learn how to do this in terms of real applications, or just for the case of understanding how NMR quantum computing does. It is just to understand that it is not a case which is very simple, but it turns out that there are ways of making sure that you can get to a result which would be sort of like what you would be expecting, or where you would be starting off as a simple case. Now, unitary transformations are the ones which are applied using quantum logic gates. NMR technique provides a universal set of Hamiltonian that can be used to implement any unitary evolution, including quantum logic gates. So, the building of quantum logic gates is very similar to designing conventional NMR pulse sequence, and therefore, it is something which has been possible to be done. As I mentioned before, in the principle of the NMR was that you would be essentially applying RF pulses to do the operations where you would do spectroscopy with it. In this particular case, instead of doing that as a spectroscopic tool, you would be essentially designing logic gates which are the NMR, which are in tune with designing the NMR pulse sequences that is used for spectroscopy in the conventional NMR case. The simplest gates are rotations about the axis and xy plane, single qubit gates, and these can be implemented using resonant RF pulses. Other gates are obtained by jointly using these basic gates. Now, so for example, the unitary operations for single qubit gates can be as simple as the X gate, the Y gate, Z gate, or the S gate, all of which are the simple single qubit gates that we have already known. The 2 qubit gates are of the ones which are the Hadamard, which are a result of 90-degree pulse in the Y dimension and 180-degree pulse in the x dimension. Now, just for clarity, let me actually tell you that these pulses, these 90 and these are essentially measured with respect to the area under this, and this is these are on for a certain time, on off, and this is the omega which is being applied. So, omega t, the area under this pulse, omega t, the area is a dimensionless number, and this dimensionless quantity is being represented by 90. So, basically it is pi by 2, pi, or some of this depending on the product of these two numbers. So, that is how the Hadamard gate turns out to be a sequence of 90-degree along the y axis and 180-degree along the x axis. So, there are two axes that can be utilized. So, the field is propagating along the z dimension, as we have discussed. This is the z dimension applied field, B or H, whichever way you look at it, and the x and y are the ones along which the RF is being applied. So, the coils could be used along these dimensions, and that is how these coils are being applied for the RF pulses of 90 pi, 180 pi, and so on and so forth. C naught is of a different kind of gate which is being discussed here. So, the quantum circuits can have control knot which can go along and provide all the different directions of applying the fields. There can be control phase gates which are just rotation gates, and depending on how these pulse sequences are being used, it can generate these kinds of gates. So, in control knot in NMR essentially works in the principle that you are applying these fields, applying these so that they can undergo the spin flips, and if they are going spin flips, then you see the Z pulse or something like that. So, here for instance, if the spin B is up, then it undergoes this possibility of putting one through the other, and then there is this delay which is very important, because this delay essentially allows the system to relax. If you are in the z dimension, if you put it back in the x dimension, it can fan out and relax, and that delay is the one which takes care of the fact that it will be actually utilizing that as a part of its pulse cycling. So, here it is a y 90-degree pulse followed by a delay to give the half coupling, JAB coupling, and then it is again an x a 90-degree pulse. If the spin B is down, then you provide a different way of doing this possibility. So, this is sort of like if you have a 2-spin system, then you have a flip A if B is down and vice versa. So, this is how generally a RF pulse sequence would look like, for instance, in a real situation for a carbon 13. So, if you notice, the carbon 13 is one which has the spin, proton has the spin, and fluorine 19 has the spin. All these three are spin which are going to interact in terms of the spin cases. So, we have three different cases, and based on these three, it is being used to do the RF pulse sequences to do this kind of thing. So, these are basically certain examples coming from research which we are not going to discuss in detail. We are just showing it to you so that you understand that it is possible. We will perhaps not be able to get into the we will not be able to get time to get into the details of these. These are just to show that these things in reality work out, and this is how they kind of look like, where you are providing the pulses and how they are coming in different windows and time scales and how they interact and how you get these things to get to the simulation of what you are looking for. So, this is a case to show how you can generate XY Hamiltonian and so on and so forth for a molecule of this kind. So, finally, the NMR computer also works with the idea that you are working on an ensemble of spin, which is why the measurement principle is very, very important. It produces an observable macroscopic signal which can be picked up by a set of coils positioned in the XY plane. The signal measures the change in the rate of the magnetic field created by a large number of spins in the sample rotating around the z axis, called the free induction decay, as we had mentioned earlier, and this free induction decay is then Fourier transform to get to the result. The magnetization detected by the coil is proportional to the trace of the product of the density matrix with the sigma plus, which is basically sigma x plus I sigma y. So, this enables the detection of the magnetization which is being read by the coil, as it is proportional to the trace. And in terms of measurement, the schematic of the diagram looks like this. You have this sample tube which has the liquid sample in it, which is being subjected to the static magnetic field. So, B0 has been showed here, and these are the RF coils which are along the dimension which gives rise to the XY plane, and the capacitor filters the signal out. There is a directional coupler, and with which we can actually have the signal being controlled and provided through the RF oscillator by the help of a computer. So, this is how a typical NMR spectrometer, this is 300 megahertz Bruker spectrometer looks like. There are many different versions of it nowadays. There are 800 megahertz NMR spectrometers which are very powerful compared to these, and it can do a lot more interesting work with it. The molecular selection for NMR quantum computing have to be also done very carefully. Desired properties are for the case of spin half systems, which are, say, for example, proton, carbon 13, fluorine 15, nitrogen 15. There can be, they need to have long relaxation times. It could be useful to get heteronuclear or large chemical systems, so that you can also use required to make spins of the same type addressable. You need to have good J coupling network, so that you can actually work with them and make them happen, and you want them to be stable, available and soluble in the system that you are looking at. It was used. It has been shown with the NMR quantum computing. Grover-Sulch algorithm has been shown, quantum Fourier transform has been shown, Shor's algorithm has been shown, Dawes-Joyce algorithm has also been shown, order finding, error correction codes and dense coding has been shown. The typical setup essentially, if you look at it a little bit more close, has this kind of setup, which has these electric field as I just showed here. So, this is the magnetic pole pieces, in which the is a permanent magnet, and then there is this superconducting magnet which is also used along with this to make sure that this one works properly. This is externally applying an oscillating magnetic field to the spin will gradually move to the state from down or up and vice versa, and this is how these gates are being done. So, ultra high sensitivity of NMRs have also been developed, and people are working on this area also to try to see if this can make things work better for NMR. the RF and the magnetic field availability is the most important thing in these cases. The signal to noise ratio is dependent on the amount of magnetic field that can be applied also. So, the higher the magnetic field the better, and so that is one of the basic ideas here. So, here is a simple cartoon of how things work. There is the, so in this particular case, for instance, the carbon and the proton in the chloroform, as I had discussed earlier, one of the proper molecules which were used for 2 qubit system was one of the first molecules which was used for quantum computing to show Hadamard transform happen by using this chloroform molecule, where the carbon and the proton was used, and the radio frequency pulse was used to address the hydrogen nuclei and causes it to rotate to form a 0 state to a superposition state. Interactions through the chemical bond would allow multiple qubit logic to be performed. So, this was one of the first cases which was shown. I have already mentioned that carbon 12 has no spin, carbon 13 is the one which you would like. So, in the case of, for example, in the chloroform that I just showed, the carbon 13 and the proton shows the spin half case, and these chlorines do not have anything. It's properly designed radio frequency pulse can rotate the carbon spin downwards to the horizontal plane, and so on and so forth. The geometry of the molecule is constrained because of the way the structure of the molecule is. The protons placed within the fixed magnetic field can induce the change of direction by magnetic field that oscillates at radio frequencies, as we have been saying. Only a few millionth of a second such radio frequencies would rotate the nuclear spin about the direction of the oscillating field, which is typically arranged to lie at right angles to the fixed field. So, that is how we had shown along the right angles, 180° pulse, 90° pulse, it depends on how you are providing them at each point, and they flip or they remain in the same place. If they flip, then they actually precess, wherever they are they will precess, and that is what happens. And if the maximum precession is at 90° place, if the oscillating radio frequency lasts just long enough to rotate spins by 180, the excess magnetic field previously aligned in parallel with the fixed field will now point in the opposite anti-parallel direction. A pulse of half that duration will leave the particles in equal probability of being aligned parallel or anti-parallel, and that is the idea behind 180 pulse versus 90° pulse, and that was the area under the pulse principle that I have been showing before. So, I mean, generally whatever I have shown until now is sort of shown here pictorially, which is that after certain short time. So, this is trying to explain whatever I said in a pictorial form. The carbon will point either in one direction or exactly the opposite, depending on whether the spin of the neighboring hydrogen was up or down. At that instant, we apply another radio frequency pulse to rotate the carbon nuclei another 90°. That maneuver then flips the carbon nuclei into the down position if the adjacent hydrogen was up, or into the up position if the hydrogen was down. A basic limitation of the chloroform computer, this is what we have been discussing lately, is clearly in a small number of qubits. That is what happens in most of the NMR principles, unfortunately. The number of qubits could be expanded, but n could not be larger than the number of atoms in the molecule employed, because this is a molecule only computer. That is the point of how it works. So, this is how these sequences they have been showing in different ways, either by showing through animation or by showing the different stages. This is how it goes, and of the celebration of quantum computing by NMR, one of the largest one has been the 7 qubit computer in IBM, where they used a 7 qubit molecule alanine, an amino acid, to factorize the number 15 with Shor's algorithm, and this was done by Chuang while he was still in IBM, and this he was able to show this with the help of nuclei of 5 fluorine and 2 carbon atoms interacting with each other to provide this process of the Shor's algorithm, where he was able to factorize the number 15. We have done the factorization of number 15 separately in this course to show the steps, and so it will become clear that how he applied this with respect to NMR quantum computing by using this molecule. Typical difficulties in NMR quantum computing lies in the fact that the number of qubits is difficulty in scaling. Standard QC is based on pure states. In NMR, single spins are too weak to measure. So, we must consider ensembles. That is one of the biggest thing here, which is different from the regular standard quantum computing principles. And QC measurements are usually projective. In NMR, we get the average overall molecular values. Tendency for spins to align with field is weak. Even at equilibrium, most spins are at random. That is one of the difficulties here. However, this is overcome by the method of effective pure states, and that is the reason why I mentioned a little bit on the effective pure states, pseudo pure states which have been done. Some of these sections will again be dealt with a little bit when we do more on the theory side of these principles, where we do density matrices, pure states, pseudo pure states, how they interact, how they operate, and those kinds of things. This was more to do with the implementation aspects, and with that I would like to thank you for today's class. We will take on further aspects of quantum computing in the next session. Thank you.